Welcome, tired friend, to another quiet night of stargazing with your resident astronomer. Whether you're here to learn, unwind, or simply drift into deep sleep, you are exactly where you need to be. Tonight, you and I will follow a gentle path of moonlight across the dark ocean. We will explore how our moon, that familiar cratered sphere I study every night, quietly pulls the oceans. It is a slow, steady gravitational tug, not unlike the heavy way your eyelids might start to feel right now. Before we launch on this lunar voyage, I would love it if you gave the video a gentle like. It helps this cozy little space channel reach more fellow stargazers. And if you feel like joining me at the observatory for more cosmic bedtime stories, hitting that subscribe button means a lot. If you're feeling extra chatty before the sleep kicks in, let me know down in the comments where your telescope is pointed and what time it is there. It is always wonderful to see our quiet little astronomy community stretch across time zones. Now I will do my best to keep the astrophysics soothing and not too intense. But if you do find yourself lying awake picturing tidal forces and deep orbital mechanics, well, at least you will have some real astronomy to ponder while the moon orbits us. So settle in, let your blankets wrap around you like warm ocean foam. Take a deep breath and let us begin. Picture a distant beach at dawn. The morning sky is barely blushing with light. The cool wind whispers, and those slow waves creep up the sand, almost like they are stretching out after a long, dark night. It is peaceful, rhythmic, almost like the ocean itself is breathing in and out. That is the tide, quiet, constant, older than humanity. But beneath this calm morning, ritual hides a story of immense, invisible cosmic forces. A beautiful planetary choreography that has been playing out for billions of years, and the main dancer here is our very own moon. In plain astronomy terms, the tides are just the regular rise and fall of global sea levels, but they are far more complex than water just sloshing back and forth. They are not driven by the wind, passing ships, or the ocean simply getting bored and deciding to shift its weight around. They are born from an intricate gravitational dance between Earth, the moon, and our sun. An endless cosmic push and pull that shapes the very heartbeat of our planet. Twice a day, without fail, the vast sea retreats from the shore and returns. This cycle is so regular, so perfectly dependable, that early sky watchers tracked it for thousands of years. Ancient fishermen in China and Mesopotamia planned huge harvests by it. Medieval monks timed their daily prayers to it. Entire coastal cities were built and sometimes destroyed because of it. But why does it happen? Why does the ocean keep rushing back and forth like it is late? To really grasp this, you and I need to picture Earth not as a solid rock, but as a giant water balloon wrapped in a thin crust of land. Now picture the moon through my telescope, silvery and steady, pulling on that water balloon with its immense gravity. It is not a violent yank, but a very subtle, endless tug. Lunar gravity pulls the ocean towards space, creating a massive bulge of water on the side of Earth facing the moon. That becomes our very first high tide. But here is where the astrophysics gets weird in a wonderfully sleepy sort of way. There is a second bulge on the exact opposite side of the globe. The dark side facing away from the moon. Wait, what? How can the moon pull water toward it, yet somehow create a giant bulge on the far side? This is one of those quiet moments where the universe just loves showing off. While lunar gravity pulls the nearest water toward it, the solid Earth itself also gets pulled slightly toward the moon. But the water on the far side lags behind a bit, like a sleepy cat refusing to follow the family upstairs. This delay creates that second watery bulge. Not because the moon is pushing water away, but because it is simply not pulling it as hard as it pulls the Earth's rocky center. That subtle difference in pull, what we astronomers call a tidal force, physically stretches the oceans into a giant oval shape. One ocean bulge faces the moon, the other points away. As our Earth spins beneath this watery distortion, different coastlines rotate into and out of these bulges, creating high and low tides in a beautiful rhythmic pattern. It is gravity's quiet little masterpiece, and this silent orbit happens constantly. Even as you rest there now, warm under the covers, the moon is pulling the oceans. Somewhere in the dark, a sandy beach is being uncovered. A fishing boat rocks a little lower in the harbor. A small crab decides whether it is safe to crawl out from under a wet rock. The exact time between these high tides is 12 hours and 25 minutes, just a little over half an Earth day. That happens because the moon never stands still. As Earth spins, the moon is also orbiting us, moving a tiny bit further along its path every single hour. So every high tide is slightly delayed compared to the exact one before it. If you and I set up a telescope by the coast to track high tides, we would notice them shifting, arriving about 50 minutes later every single day. The moon is nothing if not fashionably late. Now, not every single place on our planet experiences this exact same tidal rhythm. Some shores get 2 high tides and 2 low tides daily. In our field, we call this a semidiurnal tide. As we scan the globe, some places only see a single daily swell, a diurnal tide. Other coastlines are entirely irregular. We classify these as mixed tides, where the daily peaks and valleys shift wildly. It all comes down to geographic position, coastal shapes, and ocean floor contours. Honestly, the sea is as stubborn as the cosmos itself. But no matter your longitude, tidal forces are a constant hum beneath life's surface. They shape marine biology, they steer coastal weather. They have guided ancient animal migrations and early human settlements alike, and as scientists, we love their predictability. We can map their cycles centuries into the future. Few phenomena in the universe are quite so reliable. There is a deep comfort in that certainty. While earthly life feels chaotic, our oceans still track lunar phases twice a day. It is an orbital lullaby, playing softly on repeat across billions of years of planetary history. Through my telescope, the moon looks cold and distant, but it is hard not to feel affection for our celestial companion. It has been tugging at Earth's waters long before the very first fish discovered a tide pool. It has guided early sailors, inspired stargazers, and helped stabilize our young planet's wild rotation. Without the moon, our days would fly by in hours. The climate would be chaotic. We owe everything to that tiny, cratered rock. So as you and I listen to this cosmic rhythm, picture those ocean currents shifting far away, unseen but mathematically certain. Picture the moon aiming its pale, cratered face toward us, whispering gravity across the void. Imagine the water creeping up the shoreline exactly as it has for eons. It is the ocean exhaling, the planet resting, and our moon exerting its gentle orbital pull. All woven into an elegant, ancient celestial mechanics system, and it keeps sweeping across the globe tonight. If you lay completely still, so quiet you can actually feel the deep thrum of your own pulse, you might begin to sense an invisible physics acting all around you, a constant, silent background force. Gravity, the quiet bond anchoring us to the ground, holding the seas intact and keeping the moon locked in its delicate orbital dance around us. It never rests, not even when you are curled up under a warm blanket tonight. Or staring out your window at dawn. You and I rarely notice it, but tonight we are going to examine the cosmos because those tides, the rhythmic swelling of the sea, are really just our planet's oceans answering a very persistent invitation from space. The pull of gravity. In astrophysics, we define gravity simply as the attraction between any 2 objects possessing mass. The denser the mass, the stronger the pull. Technically, human bodies exert gravitational force too. Though unless you are secretly built from a collapsed neutron star, nothing is going to orbit you anytime soon. Our Earth, conversely, is incredibly massive. It has enough bulk to anchor us down and keep the moon firmly in its orbit. Sir Isaac Newton mapped this out beautifully back in the 1600s, watching that famous apple fall. He calculated that the exact same invisible thread pulling the apple down was keeping our lunar neighbor from drifting off into the deep dark. Our planet pulls the moon, but celestial mechanics goes both ways. The moon pulls right back. It does not tug evenly. It pulls hardest on the oceans because water is far more willing to bend than solid bedrock. A slow planetary tug of war, the moon never yanks. It whispers across the vacuum, drift closer, and the global ocean listens. This creates a noticeable swell of water on the lunar-facing side of Earth. That is our first high tide. Meanwhile, directly across the globe, a second high tide forms, and the physics behind it is surprisingly peculiar. You and I should look at this far side bulge for a moment, because gravity is about to get sneaky. The moon strongly attracts the closest water. but it also tugs the solid planet itself, the crust and mantle, just slightly less than that near-side ocean. The distant water on the far side, however, barely feels the lunar gravity at all. So physically speaking, it drags behind. The whole Earth shifts slightly toward the moon, making the far side ocean appear to stretch backward into space. Presto, a second crest. That water is not pulled outward, but rather left behind by the moon's distant embrace. We astronomers call this differential gravity. It is honestly one of the most elegant, quiet features of the entire cosmos. Gravity does not just pull everything inward, it pulls different layers with completely different strengths. That exact imbalance sculpts the global tides. To visualize it, imagine slowly stirring a pot of soup with a breadcrumb floating on top. As it swirls, the broth behaves totally differently depending on its distance from the spinning center. The crumb lags or surges depending entirely on the rotation. The ocean mimics this exactly as Earth rotates beneath the moon's gravitational field, because we never stop spinning. While our moon completes an orbit roughly every 27.3 days, Earth does a full rotation in 24 hours. Looking through my telescope, it looks like the moon just glides across our sky, but really our planet is spinning beneath its heavy gravitational pull. As our spinning world rolls under those two massive tidal bulges, one facing the lunar surface, the other pointing into deep space, we see high tides rolling in, and right between those massive ocean swells, the water retreats into quiet low tides. It is a beautiful planetary dance. You and I might wonder, with such immense gravity, why do the oceans not just fly toward the moon? Why no massive waves launching into the dark void? The answer lies in cosmic balance. That steady pull toward the moon fights our planet's own heavy gravity, firmly anchoring our deep oceans exactly in place. The whole Earth and Moon system stays locked in a gentle, endless orbit. It relies on the very same laws of physics Isaac Newton mapped out centuries ago. We also have centrifugal force acting in the background of this elegant astronomical recipe. When our world and its moon drift around their shared center of mass, which rests slightly beneath our planetary crust, that steady turning motion creates a very gentle outward push. That push forms the ocean bulge on Earth's far side, countering the lunar pull. We get 2 daily high tides from a single moon. Gravity does not just command the seas, it actually shapes the solid globe itself. The very crust we walk on slowly rises and falls a few centimeters under these vast cosmic pressures. We astronomers call it Earth tide. It will not spill your coffee, but it proves that nothing in the cosmos is ever truly still. The moon plays the starring role here, but it is not the only celestial actor. The sun heavily impacts our planet too. It rests 400 times farther out in the solar system, but its sheer mass is staggering. Its tidal power equals about half of the lunar pull, whenever the mighty sun, moon, and Earth perfectly aligned during a full or new lunar phase. Their shared gravity fuels extreme ocean extremes. We label these spring tides, not for the season, but because the heavy water leaps far higher than usual. Whenever the sun and moon sit at right angles, those competing gravitational fields actually fight each other. Bringing us calm neap tides, the sun plays its part, but our nearby moon will always be the beautiful maestro of the dark seas. Looking up tonight, you might feel the sheer weight of all this science. Or maybe the soothing weightlessness of space. These astronomical forces are incredibly ancient, yet entirely peaceful. They never roar or rush. They drift across Earth with silent persistence, lifting deep seas, gently shifting huge continents. Rocking sleepy vessels in distant harbors, gravity is the universe whispering to us, and the tides simply whisper back. The moon drags the water close, so we should only see one daily high tide, right? A single massive wave trailing the moon like a dog. It sounds logical, but the cosmos, as usual, has vastly different plans. Almost everywhere gets 2 high tides daily, one when the lunar surface sits directly overhead, and a second wave 12 hours later from the other side. How does this happen? It might seem like the moon is stretching both sides of our globe simultaneously, which feels like the universe is breaking its own rules. But this is where orbital mechanics become beautifully strange, so stick with me. We are going to unpack this puzzle together. Earth is no solid rock. our world, especially the deep oceans, acts like a soft, constantly spinning, sloshing water droplet. When lunar gravity hits our atmosphere, it does not grab the whole planet evenly. Water facing the moon feels a far stronger tug than the solid planetary core. Meanwhile, Earth's heavy crust, the forests, mountains, and our observatories all pull harder than those dark waters hiding on the far side. We astronomers call this uneven tugging a differential force. It solves the mystery. The moon is not just pulling the sea like rubber. It means various layers of Earth simply fall toward the moon at totally different speeds. So the near ocean surges upward. Meanwhile, the heavy planetary core gently drifts toward that lunar pull as well. The far ocean lags behind, creating a second swell. Picture spinning around holding a massive water balloon. The fluid inside warps and sloshes. You are not squeezing it. The sheer motion and invisible forces stretch it out. That is our planet, sloshing quietly under the moon's steady, watchful gaze. Two bulges exist. One faces the lunar surface, the other points into dark space. As our world spins, continents drag through these standing bulges, delivering two daily high tides. In between, the dark water simply recedes, flowing away to feed those distant oceanic swells. But you might be wondering if two ocean bulges fuel these tides. An Earth spins once every 24 hours. Shouldn't they hit exactly 12 hours apart? On paper, yes. In reality, not quite. As an astronomer, I see tides ignore Earth's clock. They track lunar schedules. The moon orbits our planet exactly how Earth spins, finishing one full revolution roughly every 27.3 days. For us observing from below, Earth must rotate just a tiny bit further every single day to catch back up with our orbiting neighbor. It takes roughly 24 hours and 50 minutes for any spot on our globe to realign with the moon's gravity. In my field of astrophysics, we call that a lunar day. Because of this orbital dance, high ocean tides hit 12 hours and 25 minutes apart. That is why seaside tides shift slightly later every day. From my cosmic perspective, it feels like the moon is always slipping away, forever arriving fashionably late to the shoreline. Yet not every coastline responds to this celestial pull equally. If we observed a perfectly smooth, continent-free Earth, tidal forces would look beautifully symmetrical. But our rocky planet is far from a flawless, uniform water world. We map rugged coastlines, deep bays, islands, ridges, and ocean trenches. These geographic features warp the water's flow. Along the North American East Coast, for instance, coastal tides follow a highly predictable semidiurnal rhythm. That means too high and too low sea levels per lunar day, peaking at nearly identical heights. Look down at the Gulf of Mexico, and you observe a diurnal pattern. Just a single high and one low tied across the entire lunar day. Other global regions show mixed tidal phases. Two highs, two lows, completely unequal scales. It seems planetary oceans truly love a bit of chaotic improvisation. Local planetary geography matters immensely. Narrow bays deeply amplify the tidal range, forcing massive ocean swells into restricted, entirely tight spaces. That is exactly why Canada's Bay of Fundy becomes an anomaly, producing towering ocean crests that easily breach 16 meters high. Meanwhile, the heavily landlocked Mediterranean Sea displays barely any noticeable tidal shifts at all. It resembles deep water restricted inside a cramped box. Then we chart amphidromic points, unique oceanic zones where tidal levels essentially never change at all. These serve as the calm centers of rotating tidal nodes. The sea avoids surging vertically, opting instead to slowly swirl in a very gentle circle. If you hovered directly above one, you would entirely miss the lunar tide quietly moving beneath you. It acts like the hydrosphere's way of balancing perfectly still on a spinning carousel. To make orbital physics more fascinating, our home planet is not perfectly spherical either. It sits slightly flattened across the poles and bulges wide at the equator. That creates uneven planetary gravity, deeply shifting our oceanic tidal mechanics. So, our daily dual high tides aren't merely the moon yanking invisible strings like some simple cosmic puppeteer. Let's step back. We are watching lunar gravity, Earth spin, outward centrifugal forces, and landmass shapes all grinding together in beautiful mechanical harmony. It functions less like a rigid ticking clock and far more like a sweeping, slow-motion waltz. a cosmic dance spinning elegantly for billions of years. Throughout it all, the oceans obey. Deep water shifts, surges, and recedes, falling perfectly into rhythm with the moon's relentless gravitational hold. It forms a cycle ancient navigators tracked for centuries, yet it remains so fragile that minor geological shifts can totally rewrite the tempo. And it stays so quiet that you might stand on a dark beach, toes buried, entirely blind to the immense mechanics dragging the ocean upward. But my instruments know it exists, silent, unseen, and unyielding, much like time or moonrise itself. And if the moon headlines this orbital show, our sun acts as a booming guest star, carrying massive gravitational weight. A star that stays somewhat quiet mostly, but occasionally shakes the entire planetary foundation. Although our moon primarily steers the tides, the massive sun steps in too, layering its own intense gravitational waves into this delicate fluid system. United, these celestial bodies spark massive crescendos and nearly silent pauses in the ocean's endless orbit. Let me lay out the sun's metrics. It is staggeringly huge, sitting roughly 27 million times heavier than our rocky lunar companion. However, it burns 400 times further out in the dark void, and this is exactly where orbital physics truly shine. Since gravity decays across vast distances, solar tidal influence naturally falls short of the moon's grip. Even with a massive plasma core, the sun provides just 30 to 40% of our standard lunar tidal strength. Still, that orbital push matters. When sun and moon align, sea levels turn totally extreme, flooding higher up the shore and draining remarkably far back. We map these events as spring tides, a term totally unrelated to the blooming season. The name borrows from an Old English root meaning to leap. In my observations, the planetary oceans quite literally launch into rapid motion here. These huge shifts strike during full and new lunar phases, right when Earth, Moon, and Sun snap into perfect alignment. In our field, we call this syzygy. You and I can picture this beautiful cosmic geometry perfectly. See those massive spheres locked in space, pure gravitational pull straining from dual directions in utter harmony. Lunar tug and solar gravity merge, forcing significantly higher crests and dramatically lower troughs. The total tidal variance expands far outward. Through my telescope, you and I watch coastlines shift. A full moon spring tide happens when Earth sits exactly between our sun and moon. The star pulls one way, while my lunar focus pulls the other, leaving our home planet caught in a silent gravitational tug of war. But during a new moon phase, I see both celestial bodies align on the same side, pulling together in perfect cosmic sync. Both alignments dramatically amplify the tidal swell. The ocean reaches farther, leaving heavy stretches of wet sand. Then come the neap tides. I think of them as the ocean exhaling after those extremes. I chart these during the moon's first and third quarters, when the sun and moon form a strict right angle with our planet. Instead of combining their immense gravitational force, the two bodies cancel each other out. The star tugs one way, the moon another. Caught in this orbital geometry, the ocean simply shrugs into a calmer rhythm. Neap tides bring lower highs and higher lows. The usual oceanic drama tones down into a quiet, moderate, and deeply relaxed coastal pattern. It is as if the water takes a long nap between cosmic performances. This cycle tracks the lunar phases I study every 29.5 days. Twice a month, the ocean stretches to its highest and lowest limits. And twice a month, the waters deeply relax. It is a cosmic pulse oceans follow like a clock. And what a massive clock. For centuries, coastal dwellers and sailors have lived by these astronomical charts, understanding that precise timing is everything. Before my colleagues launched satellites, spring tides meant the difference between safe harbor and a wreck. A 1700s fisherman knew the full moon brought heavy, deep currents. A true opportunity if navigated well, or a fatal hazard. Even now, cities like Venice or London carefully track these alignments. In Venice, combining spring tides with storm surges and rising seas brings heavy floods, transforming old alleyways into dark, waterlogged corridors. In London, the Thames Barrier, a brilliant piece of modern engineering, rises against those intense spring tides to shield the city from deep waters. But this orbital dance brings more than danger. These tides also deliver abundance. Along estuaries, they drag rich marine nutrients far inland, nourishing our fragile coastal ecosystems. Small crabs scuttle. Birds feast and salty mud plants breathe deep. Even now, beachgoers time their days around the gravitational clock I study. Low tide reveals hidden worlds. Rocky pools overflow with starfish, sea anemones, and tiny hermit crabs. Temporary sandbars rise where I only saw deep water before. Children splash into pools resembling alien landscapes. The rhythmic lunar pull becomes the rhythm of life itself, completely predictable. Here is where it gets complex. You and I know giant spinning space spheres are never simple. The exact strength of these tides is heavily swayed by the elliptical orbits of both our Earth and Moon. The lunar orbit is not perfectly round. When it swings closest to Earth, a point astronomers call perigee. Its gravitational grip spikes. Combine that perigee moon with a spring tide and a severe storm, and you get a towering perigean spring tide or king tide. These are the massive surges that turn heads and occasionally top our seawalls. Yet even at their most violent, I find something deeply soothing about these orbital waves. They prove the universe runs on patterns, vast and quiet celestial cycles, repeating with flawless musical precision. The moon waxes and wanes, the sun rises, and our oceans follow their cosmic lead with endless patience. Lost in our glowing screens, we forget we are part of a massive celestial ballet, that the exact same star, warming your skin each morning, is also silently dragging trillions of tons of seawater across our blue planet. That the bright moon hanging above your roof is lifting entire oceans without making a single sound. So next time you and I watch a bright full moon pull the sea back to reveal shining shells, remember we are witnessing the raw pull of our cosmic companions, two massive orbs moving the water in an endless gravitational duet. If my home planet were perfectly smooth and covered in endless water, charting tides would be a very simple affair. Just two highs and two lows sloshing back and forth with the steady tick of a sleepy metronome. But the globe I study is anything but smooth. It is a lumpy, tectonically restless, beautiful spotted marble. Those heavy landmasses, deep ocean basins, twisting coastlines, and underwater. Mountain ranges force the sea to dance a complex tune. Let us examine a geographic detail surprisingly easy to miss. You and I usually look up at the stars, but down here, our oceans are vast. The Pacific alone plunges 19,000 times deeper than a bathtub. Far below, the seafloor is scarred with dark ridges, canyons, and deep trenches. These submerged formations shape how tidal forces move across our planet. I don't mean those dramatic crests you see crashing on sunny beaches or starring in surfing films. To my eyes, tides are truly planet-sized waves. They are massive, slow-moving bulges of water, endlessly circling our spinning blue globe. They never rush, instead they stretch out with enormous cosmic wavelengths, sometimes spanning over 12,000 meters across the sea. When lunar waves hit earthly limits, coastlines, rocky peninsulas, or scattered islands, they bend, reflect, and either magnify or quietly fade out. That is why ocean tides shift wildly across the globe. Some shores feel the moon's pull with two equal high and low tides every single lunar day. Other shorelines receive just one of each, while some coasts witness a deeply mixed tidal pattern. Two high waters and two low marks, all reaching vastly different earthly heights. It all comes down to the shape of the ocean floor, the angle of the coast, and how lunar energy navigates the complex maze of our continents. Look at the Bay of Fundy up in Canada. It is a narrow, quiet inlet tucked right between New Brunswick and Nova Scotia. This bay is famous for colossal sea level shifts, rising over 16 meters or 50 feet. Why such a dramatic cosmic reaction? The bay's funnel shape forces all that lunar energy into a tight, shallow space. It amplifies the wave, almost like a child splashing bathwater. The rocky coastline aligns with the moon's tidal rhythm so perfectly that the dark water naturally begins to resonate, stacking higher with every lunar cycle, just like pushing a playground swing at the perfect time. Pure ocean physics with flawless cosmic rhythm. On the flip side, consider the Mediterranean Sea. It sits nearly trapped by land, only linked to the vast Atlantic by the narrow Strait of Gibraltar. That narrow bottleneck chokes the flow of orbital energy moving into the Mediterranean. As a result, the tides barely shift, rising just a few centimeters. Strolling the beaches of Nice or Naples under the stars, we probably wouldn't notice a thing. The water simply lacks the space to breathe and expand. Follow me to the amphidromic points, the absolutely perfectly quiet centers of our tidal world. Deep in the open ocean, these are strange pockets where the tide seems frozen in time. The water level barely rises or falls at all. Instead, the tidal pull slowly rotates around this dead center, much like dark water swirling endlessly around the middle of a spinning vinyl record. We map these swirling patterns, known as amphidromic systems, in ocean basins across the entire globe. If my boat were drifting right above one beneath the night sky, I honestly wouldn't feel the tidal shift at all. Meanwhile, hundreds of kilometers away, distant coastlines would be feeling that daily ebb and flow like perfect clockwork. This strange rotation adds another beautiful layer of planetary complexity. These waves are deeply shaped by the Coriolis effect. It's the same force that sets massive storms spinning. As our world turns, moving air and oceans drift right in the northern hemisphere and drift left down in the southern hemisphere. That planetary curve gives tidal currents their smooth, whirlpool-like spin around those quiet amphidromic points. The whole ocean spins like a massive, sleeping water wheel, driven entirely by celestial gravity and the Earth's steady rotation. And then we must consider the magic of resonance. Just as acoustic instruments hum at precise frequencies, our oceans do the exact same thing. Certain rugged shores are literally tuned to the invisible frequency of the moon's gravity. When an incoming tide perfectly matches the natural rhythm of a quiet bay, resonance takes over, violently magnifying the ocean's total tidal range. It is like hitting the perfect note on a piano and watching the strings vibrate. That planetary harmony explains why some waters surge violently, while others barely whisper against the sand. We also can't ignore the actual shape of the dry land resting above sea level. A soft, sloping beach reveals massive changes in the shoreline with every lunar tug, far more than steep, rocky cliffs. The exact same vertical shift might uncover hundreds of feet of wet sand, or it might just quietly splash against an ancient rock wall. That is why certain coastlines seem to vanish and magically reappear under the moon, while others look completely untouched as the Earth spins. Lunar tides change more than just water depth, they steer the currents, as these massive bulges sweep past islands and deep into estuaries. They generate violent flows, sometimes possessing enough raw planetary force to physically reverse rivers. The Severn Bore-Over in England is a tidal surge pushing upstream in the River Severn, drawing brave surfers and curious watchers to its muddy shores. This dance between celestial gravity and earthly geography shapes all marine life. The intertidal zones, those strips of land drowned at high tide and baked at low tide, are among the most vibrant biological habitats on our entire planet. So you and I know the width of those zones depends entirely on how far the tide retreats. In places with massive tidal ranges, whole biological worlds rise and sink with the sea, adapting to intense daily shifts in temperature, salt, and oxygen. To us astronomers, our planet is no passive partner in this celestial waltz. Earth actively shapes, warps, and amplifies the quiet gravitational whispers from our moon. The ground beneath our telescopes might feel solid and perfectly still, but really, it is a complex stage bending every note of that tidal song. Next time you visit the ocean, watch how waves trace the shoreline. Notice exactly where the water reaches and how it fades. Deep below is an invisible terrain of hidden mountains and dark valleys. They guide the ocean in ways we miss, but the moon feels clearly. It turns out, even orbital gravity loves a good landscape. Looking through the lens, our moon is a quiet, loyal companion. It glows with borrowed starlight, tugging the oceans like a patient, cosmic conductor. But their bond was not always so calm. Like any ancient partnership, Earth and our lunar neighbor have deeply changed each other over time. Far from a static rhythm, planetary tides have evolved across the eons. The tides we observe tonight are just one brief note in a grander song. To truly grasp their history, you and I must rewind the cosmic clock. Not just thousands of years, but billions. Back to the raw, molten beginnings when early Earth formed and our young moon was just born. forged from the violent debris of a collision between early Earth and a Mars-sized object named Theia. Out of that fiery chaos, the moon emerged red-hot, orbiting much closer to our young world. 22,000 kilometers away versus today's distant 384,000. With the lunar body hovering that close, gravitational tides were wildly extreme. Its heavy gravitational pull gripped our oceans tightly, creating massive tidal bulges that dwarf anything we map today. Early Earth faced monster tides hundreds of meters tall. They sloshed with such violent force that raw coastlines were totally redrawn every single day. The sea did not calmly lap the shore, it surged and roared. Our planet's rapid rotation speed only magnified the sheer celestial drama. One single day on that early planet only lasted 5 or 6 hours. With such a rapid spin, landmasses swept through those immense tidal bulges constantly. Picture enduring the complete high-to-low tide cycle several times in just one day. A dizzy world racing beneath a giant, looming moon, pulling up entire oceans like a frantic cosmic puppeteer jerking on massive invisible strings. But the cosmos always seeks balance. Slowly, the deep friction from those surging ancient waters began acting like a gentle cosmic break. Each time those towering oceans bulged and the seabed dragged beneath them, water friction quietly drained a fraction of momentum from our spinning home. That stolen rotational energy never vanished. It transferred directly out to our moon, gently nudging it higher into its starry orbit. And so our pale companion began slowly drifting away into the dark. It is still drifting, honestly. Let's look at the math together. Today, the moon recedes at roughly 3.8 centimeters yearly, about the speed your fingernails grow. It isn't exactly sprinting into the void, but across deep astronomical time, that orbital drift adds up. That expanding distance weakens the moon's gravitational hold on our oceans, gradually leaving our modern tides smaller and incredibly subdued. Meanwhile, our own rotation continues slowing down. This 24-hour day we enjoy is actually quite new in geological time. Hundreds of millions of years ago, a planetary day spanned just 22 hours. And if we somehow cast our telescopes a few 100 million years forward, your very distant descendants might watch the sun set on days lasting 26 or even 28 hours. It is a cosmic trade. The moon drifts, Earth slows. The tides grow softer, far less violent, mimicking the gentle seaside rhythm we study today. Yet this slowing orbital waltz goes entirely unnoticed within a brief human lifetime. You could stargaze by the sea every evening for a century and never spot the moon's quiet departure or feel the Earth's subtle deceleration. But the deep historical record is literally carved into stone. Ancient tidal echoes survive beautifully in sedimentary rock. Down in the Bay of Fundy or parts of Australia, we study fossilized ripple marks. Quiet layers of mud and silt left by prehistoric tides tell us exactly how often the water rolled in and how. Fiercely it hit, some 600 million-year-old rocks display 400 daily layers per year, far beyond the 365 we count now. This cosmic clue proves days were shorter and years lasted longer because early Earth spun incredibly fast. These sediment timestamps, matched with old coral rings and other earthly clues, let us map the grand history of our planet's slowing spin and the moon's retreat. We are reading a very slow, incredibly patient journal penned by the planet itself. So what do you and I make of all this? The tide's future is tied to climate, not just cosmic geometry. Watching from afar as global temperatures climb and glaciers melt, we see Earth's coastlines physically shifting. Islands might shrink while new inlets appear under rising water. This all gently shifts how our planet responds to lunar gravity. Some tidal pulls will grow fiercer, while others simply fade. You and I are watching a new chapter unfold between Earth and the moon, shaped by human hands as much as gravity. Yet through my telescope, that silver sphere keeps patiently circling, guiding the tides in its ancient rhythm. It has watched our world transform for eons, and it always will. The dinosaurs gazed up at the exact same cratered surface. So did early mammals moving through ancient fern forests. Our earliest ancestors tracked its phases from shorelines that vanished millions of years ago. Through every epoch, the moon pulled at the seas, and they answered. Sometimes with roaring storm surges, sometimes with quiet whispers. Always moving, there is profound poetry in this orbital dance. Our world actually birthed its satellite through violent collision. Yet they have been locked in a gravitational embrace ever since. The moon slows Earth down, Earth pushes it outward. In return, we get the tides, the slow breath of the sea, the rhythmic heartbeat of shorelines. So when we stand by the water watching the tide roll away, we are not just seeing waves. We are looking at billions of years of celestial mechanics at work. You are witnessing a cosmic memory that is still unfolding, and you are part of it. Just a fleeting note in a vast planetary symphony, one where lunar gravity ever so quietly sculpts the ground beneath your feet. As those tidal waters return, they bring far more than just cold ocean. They carry life. It feeds and carries countless marine species, great and small, in a rhythm older than bone. The moon orchestrates the oceans, but tides power entire ecosystems. Some of the most incredibly vibrant, chaotic, and beautiful coastal habitats rely completely on this steady gravitational pulse. Turn your focus to where land meets sea, the intertidal zone. That narrow coastal strip covered at high tide and left bare at low tide. It lives a double life, half earth, half ocean, changing its entire identity every 12 hours. For the fragile organisms making their home there, survival is all about lunar timing, endless patience, and clinging tightly to wet stone. Take the common sea star, for instance. To terrestrial observers, it looks like a simple seafloor decoration, but it is actually a relentless, slow-motion predator. When lunar gravity pulls the water high, the sea star hunts for mussels, cracking open their armored shells with a methodical, terrifyingly strong grip. Once the ocean retreats, it anchors itself to a rock or burrows into the damp sand, patiently awaiting the moon's return. Feed, retreat, rest, repeat. This endless cycle is entirely choreographed by orbital mechanics. Or study the tiny periwinkle snail, spending long days cemented to coastal rocks, hiding from hungry predators in the baking sun while the tide is low. Once the rising water hits, it wakes up, gliding across wet stones to graze on fresh algae. Massive microscopic empires of barnacles, crabs, anemones, and coastal sponges thrive in this shifting lunar rhythm, each holding a unique strategy to stay wet, fed, and alive. Some creatures even link their internal biological clocks directly to the turning of the moon. Look at the grunion, a little silver fish darting along the California and Mexican shorelines. On very specific spring tide nights, exactly when lunar gravity pulls the water highest, they swim ashore. Hurling themselves from the waves by the thousands, they bury their eggs deep in the wet beach sand, safely above the normal tidal reach. Those eggs sleep safely until the next full moon orbit 2 weeks later, when extreme high waters wash over the beach, hatching a chaotic, silvery celebration. It is one rare biological marvel that genuinely makes you stop and wonder. Why would fish voluntarily lay eggs on dry land? Then there is the horseshoe crab, a bizarre survivor that looks like it crawled out of deep geologic time. Each year, right around May and June, these ancient arthropods swarm the American Atlantic beaches to spawn. They perfectly sync their massive arrival with the extreme pull of the new moon. This lunar clockwork is so mathematically precise that migratory birds like the red knot evolved to plan their massive global flights around it, while those ancient crabs deposit millions of rich eggs. Flocks fall from the sky to refuel, swallowing crab eggs by the thousands before continuing their long migration up toward the Arctic. The tides act as a massive planetary conveyor belt. Whenever ocean surges flood into estuaries, they carry heavy loads of organic material, microscopic plankton, and dissolved minerals. This astronomical rhythm makes tidal zones incredibly productive. They become rich feeding grounds for countless species. Tough salt marsh grasses, drinking up seawater that would destroy normal plants, grow incredibly thick here, trapping sediment to anchor the shore. But you and I know it is not just wildlife answering to the moon. Entire human civilizations have risen, flourished, and fallen by these shifting celestial waters. Early humans watched the lunar phases, building fish traps in the tidal zone. Clever rock walls invited fish during the lunar pull, stranding them as the ocean receded. Off the Scottish coast in the Orkney Islands, those ancient stone traps remain. Smoothed by centuries of lunar rhythms, For generations, fishing cultures have watched the heavens, using the moon's steady pull as a secondary clock. You and I mostly live by the sun, but in Southeast Asia, whole villages run on lunar tide flows. Sailing, fishing, and gathering meals along the shore all rely on tracking that cosmic push and pull. Up in northern Europe, where the muddy seafloor stretches toward the horizon, locals drive across the exposed seabed at low tide, crossing to islands that vanish when the moon raises the ocean. I find it fascinating to watch cars drive over the ocean floor, roads erased by returning waves hours later. Down below, coral reefs also feel this lunar gravity. Those shallow reefs depend on the celestial ebb and flow to wash fresh, oxygen-rich water over marine life. The moon's rhythm balances the temperature and salt. When the tide retreats, tiny reef animals hide in shallow pools, forming little universes bursting with bright colors and quiet mystery. One single rocky basin might hold sea urchins, clownfish, and vivid purple algae. They sit huddled together, waiting for the moon to swing back and grant them fresh freedom. Then we have mangroves. Those rugged, salt-loving trees take root in the shifting tidal zones from Florida over to Bangladesh. Their twisted roots shield young fish, block heavy storm waves, and absorb carbon from our atmosphere much better than inland forests do. Without that lunar rhythm, mangroves would die out, and without them, so many coastal towns would face terrible danger from ocean flooding and soil loss. This cosmic clockwork even shapes human emotion, art, and mythology. The moon's pull has sparked poems and endless stories. We talk about the tide turning, of luck ebbing and flowing, or feelings swelling up much like an approaching high tide. This quiet link between lunar orbits and our human hearts is entirely real. It shows a deep, quiet knowing that we are bound to the physics of the universe. We might not map the stars each night like our ancestors, but the moon remembers its path and the sea answers. Together, they keep the grand rotation spinning. So when you stand barefoot at the shoreline, feeling the water wash over your ankles, remember that you're stepping inside a massive planetary clock. A clock that dictates the pulse of global ecosystems, triggers old traditions and feeds countless forms of marine life. The ocean is not merely moving, it is listening, answering the distant call of the moon. While orbital mechanics are universal, the way they warp the water across our planet is beautifully diverse. Like different dialects of a single cosmic language, tidal forces behave very differently depending on your exact coordinates. Some shores only see a gentle ripple, others endure massive, thundering walls of water. In specific pockets of the globe, the ocean jumps away from the land, only to completely disappear a few hours later. Land masses, seafloor shapes, and a bit of geographic luck combine to give every coast its own distinct reaction to gravity. Let's point our telescopes at the Bay of Fundy. Tucked between the Canadian shores of Nova Scotia and New Brunswick, it boasts the absolute highest tides on Earth. On a typical day, the bay's water levels swing up and down by an incredible 16 meters. That is over 50 feet. To picture that scale, imagine a 5-story building slowly flooding with ocean water, then emptying out twice a day, every single day. No machines involved, just pure lunar gravity at work. So why is this specific bay so intensely affected? As an astronomer, I look at resonance. The bay's specific shape and depth form a perfect basin that magnifies the incoming tidal waves. When the internal sloshing of the water inside the bay matches the exact timing of the incoming Atlantic tide, the energy builds up, just like timing a perfect push on a playground swing. Every time the moon pulls new water in, that energy stacks up, creating a breathtaking rise and drop. People visiting the bay can actually step out and walk directly across the naked seafloor at low tide, weaving around massive, towering rock columns. Then come back hours later to see those giant stones swallowed by water. This cosmic shift happens so fast, there are warning signs posted everywhere. Please get back to land before the water returns. It is solid advice, unless you really want to trigger a slow-motion coastal rescue operation. Scanning across the globe to Mont Saint-Michel in France. Gravity writes another intense story, though framed by ancient Gothic stone. This medieval abbey sits on a rocky Norman island, tied to the mainland by a simple road. You and I could stroll right across the dry sand during low tide. But at high tide, the rushing ocean completely cuts it off, transforming the space into a floating, fairy tale fortress. The water sweeps in here at the speed of a galloping horse, easily fast enough to trap anyone not paying attention. For centuries, travelers have looked back in shock, watching their safe, dry path vanish under a powerful, moon-driven surge of ocean water. Looking down at Earth, we see the United Kingdom's Severn Estuary, home to the Severn Boar. It is a rare planetary phenomenon. The moon's gravity pulls the incoming ocean tide into a wave that pushes miles upriver, defying the natural current. Surfers and brave swimmers actually gather to ride this long, curling wave as the cosmos pushes it inland. It is a tidal roller coaster powered purely by the gravitational clockwork of our solar system, but not all lunar effects are this theatrical. In some parts of our globe, like the Mediterranean Sea, the moon's pull goes almost unnoticed. From orbit, you see the Mediterranean is nearly trapped by land, with only the narrow Strait of Gibraltar linking it to the vast Atlantic Ocean. This tight planetary choke point blocks the lunar tidal flow, resulting in water shifts of just a few centimeters along those ancient coasts. Honestly, if you were not staring at the shoreline, you would never realize the tide was shifting. The sea seems completely still, as if our moon's gravitational invitation was just politely declined. But across the globe, the Kimberley coast of Western Australia takes the full brunt of celestial mechanics. Here, the ocean can rise and drop by more than 10 meters. In narrow inlets like horizontal falls, this massive lunar pull creates what looks like a raging whitewater river, except it is not a river. It is the whole ocean being dragged through tight coastal cliffs by gravity, churning the seawater into violent, raging rapids. Boats can slip through the gaps when the cosmic tug rests. But when that orbital engine revs up, it is a dangerous spectacle best viewed from a helicopter above. Yet lunar gravity also shapes human life very quietly. In Venice, Italy, the lunar rhythm triggers acqua alta, or high water, during specific seasons, mainly the autumn and spring alignments. The moon's peak pull joins shifting atmospheric pressure to completely flood their ancient city squares. Locals balance on wooden platforms, while shopkeepers frantically stack sandbags. We astronomers watch how a warming Earth makes these Venetian floods worse. Rising sea levels and extreme weather are turning a celestial quirk into a crisis. The orbital dance is no background detail here. It dictates human urban planning, architectural survival, and strangely enough, their fashion. Rubber boots are simply mandatory. Down in the low-lying atolls of the Maldives, tiny shifts in the moon's gravity create massive problems. These coral islands rest only a few meters above the ocean. The sun and moon's alignment decides whether those people have dry land to walk on or sinking coastlines. The people living there track the moon's phases just like an astronomer would, not out of curiosity, but pure survival. Their entire existence ebbs and flows with our satellite's gravity. But these planetary rhythms are not just interesting to observe. They are absolutely vital to science. Let us look closer at this together. Tracking these global lunar pulses helps my fellow scientists map deep sea currents, predict storm surges, and trace energy across Earth. Watching how the moon's drag shapes the seafloor unlocks clues to Earth's climate systems, and even our planet's deep past. By reading fossilized shorelines, we can calculate ancient sea levels, shifting tectonic plates, and even historical wobbles in Earth's orbit around the Sun, despite their differences. Tides prove that while the exact same cosmic physics govern our entire globe, the pull of the Sun, the Moon, and the spin of our world, the way water reacts is just infinitely diverse. To an astronomer, it sounds like one grand cosmic symphony played on thousands of earthly instruments, all at different tempos. From the massive floods in the Bay of Fundy to the quiet ripples of the Mediterranean, lunar gravity works in countless ways. So wherever you happen to stand on Earth, whether the ocean whispers or roars, you and I are always watching a local chapter of a vast cosmic story. A beautiful planetary tale told through water, gravity, time, and orbit. Our moon floats hundreds of thousands of miles away, yet its invisible reach shapes the edges of continents and the human lives growing along them. Twice every single day, orbital mechanics literally lift and drop oceans of water across the entire planet. Trillions of tons rising and falling like the slow breath of a living world, and all that friction generates staggering planetary energy. As long as stargazers and sailors have watched those lunar tides, we have wondered if we could capture that power. The answer is yes, in some regions we already are. Harvesting the ocean's motion, known as tidal energy, is among the oldest methods of renewable generation humanity has ever attempted. Because celestial orbits are strictly predictable, this clean power source is endlessly recurring. The moon is never going to oversleep. Even when solar panels face cloudy skies, the moon keeps pulling. Unlike burning fossil fuels, gravity does not pollute our atmosphere. The tides just keep working. Come with me, let's figure out how we actually capture power from the ocean's lunar heartbeat. We must look backward. Long before we understood orbital dynamics or built steam engines, ancient stargazers across Europe and the Middle East engineered simple tidal mills. These early structures simply trapped incoming seawater inside stone basins, while the moon dragged the tide upward. As the moon released its gravitational grip, retreating water flowed through wooden wheels, spinning stones to crush grain. These coastal setups weren't driven by ordinary streams. They were powered by our lunar companion's silent, steady gravity. We find a surviving relic in Northern Ireland, the Nendra Monastery tidal mill, resting there since the 7th century. Picture this with me. Monks used the ocean's daily breathing to grind flour, a gorgeous marriage of orbital mechanics and simple daily bread. Jumping to our modern era, the underlying physics remain exactly the same, only the machinery grew. Today, we harvest this lunar force in a few ways. The oldest method is the tidal barrage. Picture a massive wall draped across a coastal estuary, fitted with enormous steel gates. As the moon draws the ocean high, water pools behind this barrier. Once the Earth rotates and the tide recedes, that trapped sea pours through heavy turbines, creating electricity as it returns. It perfectly mirrors how we harness rivers with hydroelectric dams. Only here, the river is the ocean itself, flowing both ways. A famous example is the Rance tidal station in Brittany, France, constructed back in 1966. It remains active today, generating enough wattage to comfortably light up 130,000 homes. This is a beautiful kind of renewable grid power. It ignores cloudy skies or still wind. The lunar tide just keeps flowing. We also have stream generators, basically wind turbines submerged in the dark. Instead of atmospheric breezes, these elegant blades catch ocean currents driven by gravity. We anchor them to the dark seabed, right inside fast underwater highways of dense, moving saltwater. As the gravitational swell pushes and pulls, the heavy rotors gracefully spin, creating power. Since liquid water is roughly 800 times denser than air, even a gentle cosmic drift packs incredible force. These submerged systems carry such an elegant simplicity. They avoid massive dams or overwhelming concrete coastal infrastructure. They rest silently in the deep, rotating with the moon like drowned windmills. Another fascinating method we're studying involves artificial tidal lagoons. Think of these as man-made pools hugging the coast. Water cycles through embedded turbines as the Earth turns, acting much like a traditional barrage. However, lagoons fit perfectly in coastal regions, where blocking an entire estuary simply cannot work. We safely capture orbital energy without choking off delicate river mouths or harming coastal biology. So why is this cosmic power still rare? You and I both know the ocean is predictable, but it is deeply hostile to machines. Engineering anything in saltwater is a nightmare. That alien environment is relentlessly harsh and corrosive. Our gear must survive crushing depths, violent storms, and relentless barnacles settling in forever. Naturally, keeping this equipment running gets incredibly expensive to maintain. We also face planetary geography. Only a few specific coordinates on Earth experience gravitational tides strong enough to justify the massive effort. We require narrow coastal straits or plunging estuaries featuring extreme depth changes and rushing currents. This explains why only a select few regions, like the United Kingdom, Canada, and South Korea actively fund this specific technology. We must weigh the environmental risks too. Massive barrages, for instance, often disrupt ancient fish migrations and alter delicate local ecosystems. Shifting this natural lunar pulse can change estuary salinity, confusing fragile habitats that rely on the timeless ebb and flow. Like any planetary engineering, we must carefully balance our thirst for power against the deep scars we might leave behind. Even so, capturing a pure, rhythmic energy straight from lunar gravity remains absolutely beautiful. It feels poetic. We are taking raw energy from a passing celestial body, flowing through dark oceans right into our living rooms. It carries profound elegance and serious advantages. Unlike erratic solar or wind, orbital mechanics are flawless. I can calculate tide charts centuries ahead. That immense cosmic certainty makes feeding local power grids incredibly simple to manage. The ocean's heavy rhythm never randomly vanishes overnight. Our quiet moon simply does not skip a beat, as humanity pushes harder toward a cleaner planetary energy grid in the coming decades. Lunar tidal power will take the stage, particularly along rugged shores where we can engineer machines perfectly suited to the tides. Brilliant leaps in materials and deployment will soon make our deep-sea turbines highly efficient, much cheaper, and vastly kinder to ocean life. Soon, the churning sea could illuminate your quiet kitchen, push your morning train, or even charge the phone you are listening to right now. A gentle, sleeping power pulled from an ancient orbital rhythm, endlessly breathing beneath the waves. So the next time you and I stand by the dark waves, feeling that water tug our feet, remember the sheer energy there, true cosmic power. Not just a tiny ripple pushing seaweed around, but massive kinetic force that can ignite glowing cities. Energy born 384,000 kilometers away, a silent moon whispering to the water, and our ocean answering with every rise and fall. Tonight, you and I are going to look up. As the moon glows quietly, something extraordinary shifts across our planet. It never roars or flashes, but through my telescope, I know it moves mountains of water. This predictable pull is far more than a seaside novelty. It is the bedrock of planetary mechanics. These tidal forces are much more than rising water. In astronomy, we see it as a conversation between Earth and Moon, a soft dialogue spoken in gravity. Think of the tides as Earth answering the Moon's gravitational pull. The lunar mass tugs and the oceans line in. The math shows it is not a harsh tug on a rope, but a slow, quiet beckoning. A celestial invitation our seas have answered for over 4 billion years, and our home planet listens beautifully. Earth replies with motion, with orbital balance, and with time itself, because these lunar cycles alter far more than coastlines. They shape animal behavior and keep our planetary spin stable. At the center of it all sits the moon, quietly keeping the rhythm. As an observer of the night sky, I deeply appreciate what a remarkable partner our moon is. While the sun roars with solar flares and radiation, the moon stays quiet. It reflects instead of emitting. It drifts calmly instead of burning. And yet this silent satellite dictates the daily ebb and flow of our global oceans. It works with absolute precision, making the exact same request every day. Come closer, then release. That simple instruction builds the tidal bulges we study. But the real physics gets fascinating here. Those ocean bulges rarely align perfectly with the moon. Because Earth rotates so quickly, the water bulges are dragged just slightly ahead of the moon in the sky. That slight offset generates torque. It is a twisting force pulling the moon forward in orbit while simultaneously slowing down Earth's rotation. Through my calculations, it looks like Earth gives the moon a gentle push, offering it a little extra momentum. Because of this, I measure the moon inching away by 3.8 centimeters yearly. As it retreats, our Earth day grows slightly longer. Give it a few 100 million years, and one single Earth day will easily pass 25 hours. You and I are watching tidal locking in slow motion. Billions of years down the cosmic timeline, the moon will drift so far, and Earth will spin so slowly that only one side of our world will face it. Since the moon already shows us just one face, this heavy gravitational dialogue will finally settle into a quiet, frozen lock, a lasting cosmic embrace. But my charts show we are nowhere near that end. We live in a golden astronomical age. The moon still orbits us, the Earth spins freely, and the oceans breathe twice daily. This celestial rhythm controls so much more than sandy shores. Tides regulate our global climate. They pull heat and nutrients through deep ocean layers, fueling massive marine currents and keeping our sea life completely oxygenated. Without this lunar pull, the deepest waters would quickly stagnate. They would grow freezing cold and hostile. Tides dictate marine migration patterns, acting as a flawless biological clock for species tracking the lunar phases. Sea turtles, for example, wait for very specific tidal phases to hatch, boosting their chances of living. Plankton rise and fall with the orbital pull, feeding the fish that sustain seabirds and everything else. The whole food chain is tuned to lunar gravity. Even our earliest human calendars are space myths, and our concept of time grew from watching it. Ancient lunar charts guided human farming. Early coastal cities mapped themselves around tides. Whole languages crafted beautiful ways to describe the rising sea. Humans always knew the ocean was tied to something vast and eternal up in the sky. Quite simply, the moon made Earth what it is today. Without it, my models show Earth's axis wobbling violently, destroying our stable seasons. The moon works as a heavy gravitational anchor, keeping our planetary spin smooth. Without that balance, we would lack the steady climate needed for complex life to evolve. The moon grants our home planet its composure and calm. I find something deeply comforting about that when looking through the lens. Something so distant and completely silent holds such a massive, tender influence. We are quite literally tethered to a rock floating in space. We do not just orbit the sun, we dance with our moon. This gravitational bond is ancient, yet happens in real time. Our modern cities might blind us with artificial light, but the lunar rhythm plays on above the glow. Walk along a dark beach tonight and look out over the harbor. You will see boats rising gently against their heavy moorings. Wet sand drying into ripples, shorebirds hunting in the freshly exposed shallows, grabbing one last bite before lunar gravity pulls the water back. And maybe standing there, you and I can feel it too, the slow, deep pulse of our planet answering a distant call. The moon, our quiet orbital partner, just keeps shaping the oceans without making a sound. No loud engines, no schedules, just pure gravity and presence. If you ever feel lost or overwhelmed down here, look up. Remember that every few hours, our entire ocean rises and falls, guided by a distant celestial force you can't see. But as an astronomer, I assure you, it is always there. Our moon is quietly pulling on the Earth, and our blue planet answers through the ancient rhythm of the tides. And so, as we wrap up our cosmic journey tonight, you and I return to where we started, standing by the sea, listening to the dark waves. Perhaps now you view those deep waters with a stargazer's eyes. Not just as water rolling in and fading out, but as a beautiful gravitational duet between the Earth and the moon, an ancient orbital dance that started billions of years ago and will spin on long after us. We have drifted through planetary science, from bulging oceans and our spinning globe, to moonlit animal migrations and the slow, quiet expansion of time itself. We explored rocky coastal shorelines and sunken ocean turbines, watched monks grind grain with sea water and crabs mating under the pale moonlight. We learned that my favorite cratered moon is actually a massive force shaping our home world, and that the tide, though it feels calm and repetitive, is complex astrophysics in motion. It is constant yet never truly still, predictable yet endlessly shifting. A quiet gravity with the power to shape whole continents, feed marine ecosystems, and literally slow the Earth's rotation. Now, fellow stargazer, as you lie there resting, maybe already drifting out toward the stars, I hope the orbital mechanics of this story carried you gently into that quiet space before sleep. I tried keeping the science soft, but if your eyes are open, then at least you picked up something beautiful about our moon, the ocean, and their eternal dance. If you enjoyed looking up with me, I would be deeply grateful if you liked this video or subscribed for more peaceful space documentaries with Cosmic Veil. It supports our tiny observatory more than you know. Before you drift away, I would love to know where on this spinning globe you are. What time is it? Leave a comment below if you feel comfortable sharing. It is a true joy watching this sleepy community of space lovers ripple across different continents and time zones. So wherever you are looking up from, may your tides be calm, your skies be clear, and your dreams be guided by the same gravity that pulls the midnight sea. Good night.